To describe the transformations and do the graph, we do want to know what the parent function looks like. When I take a look at this equation, I see we have a square root there. So the parent function equation that we're going to be looking at is the square root parent function equation. That equation is y is equal to the square root of x. And if you make an xy table or know what that looks like from previous classes or previous problems, we have a starting point here at 0, 0. Goes through the point 1, 1, goes through the point 4, 2. Those are a couple of other easy points to find. And then has this shape. Starts out kind of steep, and as we go to the right, it still continues to go up, but a little more gently as we go to the right. If we compare the equation of the parent function with what we're going to be doing here in letter B, there are a couple of things that are different. One of them is that in front of our square root, we do have a 1/2, and then inside the square root, we do have a +4. The 1/2 that we have in front is called a few different things depending on the book. One of the things is that we could call this a vertical compression. Specifically a vertical compression by 1/2. Any number here that would be smaller than 1 that's being multiplied by the square root, that would give us a vertical compression. Another way that you can think of this is that this graph is going to be half as steep as the parent function. We have 1/2 in front. The parent function, it does not have any number in front, so that is like an invisible 1 in front. So the parent function, we could say, kind of has a steepness of 1 if we wanted to think of it that way. And then with this 1/2 being multiplied out in front, this is going to be half as steep. Each one of the points that we have here is going to have to be half as tall. So let's talk our way through that. The parent function graph that we just had on the previous screen, y equals the square root of x, has a point at 0, 0, has a point at 1, 1, and then has a point at 4, 2. And it looks something kind of sort of like that. And then from there, we would want to do a vertical compression by 1/2. So let's talk about what that would look like. A vertical compression by 1/2 would have all of these same points on them, but we would want the heights of each one to be half as tall. So for our equation, y equals 1/2 times the square root of x. That would be just a compression of 1/2. We'd want to take a look at each one of the points that we have here and make them half as tall. This point here, the point 4, 2, is at a height of 2 up above the x-axis. Half of that would be a height of 1. So 4, 1 is going to be one of the points on our graph after we do the compression by 1/2. This point here is the point 1, 1, and it is a height of 1 up above the x-axis. If we do half of that, that would be at a 1/2. So another point that is going to be on our graph is 1, 1/2. 0, 0, well, that's at a height of 0 up above. We still have to do half of it, but half of 0 is still 0. So 0, 0 is going to be another point on our graph. So it'll start out a little steeper, and then as you go to the right, it will continue kind of leveling off. So here's the original parent function. We want something with a vertical compression by 1/2, something that is half as steep. That would give us those 3 points. But that's not the only transformation we have in this problem. We also have a transformation based on this +4 that's there. If you have addition or subtraction inside of your grouping symbol, which the square root is, it's considered a grouping symbol, that is your horizontal shift. And if you have an x +4 inside of your parentheses or inside of your square root, inside of your grouping symbols, that's going to slide your graph over to the left. So we need to go over to the left 4 units. We've already done our compression by a half, so if I take this orange graph and I slide it over to the left 4 units, then we will have our final graph. So I want to take the orange graph that we have, and I want to slide each one of the points that we have over to the left 4 units. I have a point here at 0, 0, so I'm going to slide that over 4 units. That would be at the point -4, 0. We have a point at 1, 1/2. I want to move that over to the left 4 units. That's going to be the point -3, 1/2. And then we have a point at 4, 1. And I want to move that over 4 units. And that would leave us a point at 0, 1. So those are 3 of our points that would be on our graph. We still want it to have that square root shape. Start out a little steeper, and as we go to the right, it's a little bit more gentle. This is our final graph. The directions, we were supposed to describe the transformations. We've done that here. Left 4 units and a vertical compression by a half or half as steep. We were supposed to graph the function. So we took our parent function, did our compression, and then slid it over to the left. The last thing that we need to do is take a look at our graph for our final answer and identify the domain and the range. The domain, that's how far left and right our graph goes. This graph goes over to the left to a -4. That's as far over to the left as it goes. So our graph from left to right starts at -4, and then it goes forever to the right. So if you're writing that in terms of an inequality, our x values are -4 and larger, so x is greater than or equal to a -4. Some textbooks use set builder notation. Set builder notation starts with a wavy bracket, then your variable, and then a vertical line, and then they copy that inequality down, and then close that off with another wavy bracket. They say the same thing, just in 2 different forms. You also could put this into interval notation. We're starting at -4, and we're including that value as part of our answer. And then as we go to the right, we go forever to the right. So from -4 to infinity. All 3 of those say the same thing. We would just need to represent our answer with one of those 3. I probably would use this first one, but all 3 of them are totally fine. For our range, we want to look at how far down and how far up our graph goes. Our graph goes down as low as the height of this point right here, which is at a height of 0, and it does go up for forever. Very, very, very slowly up for forever, but it does go up for forever. So everything's 0 and higher. So our y values would start at 0 and then go up for forever. Set builder notation, we would have the set of all numbers y such that y is greater than or equal to 0. And if you're doing interval notation, we are starting at 0 and going up for forever.